Hello everyone, myself Dr. Madhu Tiwari from Department of Chemistry, Kashi Naresh Government PG College, Kanpur. In this series lecture of certificate course on spectroscopic techniques organized by Department of Chemistry, today I am going to talk about UV visible spectroscopy. So first of all, we will talk about what is spectroscopy branch deals with. Spectroscopy actually, when the electromagnetic radiation or radiation interacts with a matter, then what happens? It goes to be studied in the branch called spectroscopy. Now, what is electromagnetic radiation? So, as the name clears, electric field and magnetic field. The wave which consists of electric field and magnetic field both propagating parallel to each other, those radiations are called electromagnetic radiation. You will see in this slide the blue area are magnetic field and the green one are electric field. So both are perpendicular to each other, you are seeing here. So now there are some terms which are frequently used for electromagnetic radiation. These are frequency and wavelength. Frequency, what is frequency? Actually, per second oscillation performed by the wave is called frequency, and the unit of frequency is hertz, you know well. And what is wavelength? Actually, the in the wave, the distance separation between two maxima or two minima are called wavelength of light. It is represented by lambda, and the energy of the radiation, electromagnetic radiation, is represented by E, and which is equal to h nu, means hc by lambda. Now, what is electromagnetic spectrum or electromagnetic series? It is a series in which electromagnetic radiations are arranged either in increasing order or decreasing order with respect to frequency or wavelength or energy. One of the most emphasizing property of electromagnetic radiation is this one. When white light passes through a prism, then it gets splitted into seven constituents: violet, indigo, blue, green, yellow, red, orange and red. Means all wavelength are splitted separately, and this is an important property of electromagnetic radiation. Now, coming to the principle of spectroscopy. What is principle? Actually, spectroscopy deals two phenomena: absorption spectroscopy and emission spectroscopy. So, when the intensity means electromagnetic radiation when interacts with matter, then it get absorb some intensity and rest it will transmit. So the intensity or energy of electromagnetic radiation when plotted with the frequency or wavelength, then this study is gone through with absorption spectroscopy, and consequently when the emitted energy is intensity is plotted with the wavelength or frequency, then it is emission spectroscopy. One of the most popular example of absorption spectroscopy is UV visible spectroscopy. Infrared spectroscopy is also an absorption spectroscopy, and the example of emission spectroscopy is mass spectrometry. Now, what happens when electromagnetic radiation interacts with matter? Each and every molecule wish to be in its stabilized state, and at room temperature lowest energy state is the most stable state of molecule. So at room temperature all molecules or atoms are remain in the lowest energy state. So what happens when the electromagnetic radiation interacts with matter? These molecules absorb the intensity and go through the higher level, and the separation of energy is is equal to h nu, means h nu, where h nu is the h is the Planck constant, nu is the frequency of that particular incident light. So molecule remains in the higher state, and after some time it comes to the either in original state or in other higher level, and it in this phenomena it emits the photon of that particular separation of energy. If now if the separation is in the range of UV and visible, means 200 to 900, then it is called this study of spectrum is called UV visible spectroscopy. If the incident if this separation is less than UV visible, then it may be infrared, in the range of infrared, then it is called infrared spectroscopy, and it causes the molecule to vibrate, to be in vibration. And if the energy is even more less than vibration, FT means infrared, then it may be microwave energy, and this causes molecule to be rotated. So clearly you are seeing here that the molecule electronic energy state is highest, and which is greater than the vibrational energy state, and which is greater than rotational energy state. Now for UV visible spectroscopy, so we have studied what happens when matter interacts with electromagnetic radiation. So now we have to study UV visible spectroscopy. So what happens in UV visible spectroscopy when a UV visible radiation, UV visible range of electromagnetic radiation incident to the matter, then incident to the a solution containing a compound, then when it passes through the solution, the energy and intensity of incident radiation get reduced. So what happens, what intensity this particular compound has absorbed, it is studied in the UV visual spectroscopy. So for this we have to know about the Lambert law and the Beer law. What Lambert law state, when a monochromatic radiation, means what is monochromatic radiation, means monochromatic radiation are those radiation which consist only one wavelength of light. So when monochromatic radiation passes through a solution, then intensity of the incident radiation get reduced. So the intensity of incident light which get reduced with respect to particular thickness of the solution is directly proportional to the intensity of incident light. So the mathematical expression you will see here, that d minus di by dx is perpendicular to I, means incident intensity. So here x is the thickness of solution and I is the intensity of light. So what minus sign refers, since you know that intensity is going to be reduced, so here it is negative sign. And now when you will integrate this equation up to I is equal to 0 to I is equal to I, and x is equal to 0 to x is equal to L, it is L. So what you will get ln I by I0 is equal to minus KL. So now when in the log base 10 value, what you will get, log I by I0 is equal to minus K by 2.303 L. Now if we consider log I0 by I, log I0 by I is equal to A, means absorbance, this A is called absorbance, and this K by 2.303 is equal to E or epsilon. You in some reference book you will see this by epsilon, and this is called absorption coefficient. So this equation will be reduced to minus A, and here you will see, and here you will see it is minus EL. So both minus will cancel out, and what you will get? You will get A is equal to EL. This is the Lambert law. Now Beer law, what Beer law states, the monochromatic solution when passes through the monochromatic radiation when passes through the solution, then the intensity, you know intensity will get reduced. So the reduced intensity with respect to thickness of the solution is directly proportional to the concentration of solution. The mathematical expression for this is here minus di, again negative sign refers for the reduction of intensity, minus di by dx proportional to Ci. C is the concentration, I is the incident intensity. When further you will integrate this I from I is equal to I0 to I and x is equal to 0 to L, 0 to L, you will get this equation ln I by I0 is equal to minus KCL. Here you are seeing that it is not K because we have taken K in Lambert law. So again from the same procedure, what you will get here, E is equal to ECL or E is equal to epsilon CL. So what is epsilon here? Epsilon is the extinction. Here E is equal to molar extinction coefficient, same coefficient, and C is the concentration of solution, L is the length. This is the Beer law, and from the 1 by A is called transmittance. From this both equation you will see this T refer for transmittance, then A is equal to 1 by T from this equation. This is the Beer law. Now what is limitation of these Lambert-Beer law? Actually this Lambert-Beer law is only hold good for the dilute solution, because when concentration of solution get increased, then it is opaque to the incident radiation. When it is really opaque, then how we will get the absorbed radiation. So only it is good for dilute solution. And another limitation of this Lambert-Beer law is when the solution get dissociated, means molecules in the solution, compound in solution get dissociated or associated, and then it will not hold good. So these are a limitation of Lambert-Beer law. Now coming to the instrumentation. For instrumentation you will see here that there will be a source, and then wavelength selector, means monochromator, and then electromagnetic radiation passes through a solvent, and then it will be detected by photodetector, and then it will be studied. Now again in the second process, same radiation is passed through the sample, and this sample will consist same solvent, and then again it goes through the detector and studied. So this is the instrumentation, how UV visible spectroscopy is going to be performed, means UV visible spectra, how it is going to be taken. Now Principle of UV visible spectroscopy. The most common solvent used in the UV visual spectroscopy is ethyl alcohol and hexane solution. Ethyl alcohol is a protic solvent and hexane is a non-protic solvent. In the principle of UV visible spectroscopy, you will see electronic transitions, and this is the schematics of electronic transitions. You will see here that the lowest energy state is called sigma, means bonding, and the next one is pi, and the upper one is n, non-bonding, and then anti-bonding, and then sigma star anti-bonding. So these n pi and sigma, these are the bonding orbitals, and these sigma star pi star are the anti-bonding orbitals. So next, what type of transitions are going to be, or maybe what type of transitions are may be possible? You will see here pi to pi star, pi to sigma to sigma star, pi to pi star, n to pi star, n to sigma star, and next n to sigma star, sigma to pi star, and pi to sigma star. So out of these 6 transitions, only 4 transitions are allowed, symmetrically allowed. The 2 sigma to pi star and pi to sigma star, these are symmetrically forbidden. So out of these 6, only means these 5 and 6 transitions are not allowed transitions. So we will study this one by one. Sigma to sigma star transition. This is the you have seen in the schematics that this transition have the energy separation largest, and this occurs in the sigma bond, means CHU or CO or CN sigma bond. Now next, n to pi star transition. This occurs where in which compound there is non-bonding electron, then this transition is going to be occur. As example, C double bond N, C double bond O, and double bond O. In these functional group, n to pi star transition is going to be occur, and these sigma to pi star and pi to sigma, these transitions are energetically forbidden. Now the terms used in the UV visible spectroscopy, there are some terms. One of them is chromophore. Chromophore is actually the functional group which is responsible for the occurrence of color in the compound. And these chromophores are these are some examples of chromophores. You will surely see that each of chromophore will consist hetero bond, means this will not hetero bond, it unsaturation bond, means double bond or triple bond. So chromophores are responsible for color. And next, in case of acetone, you will see the lambda max is at 279 nanometer. While in case of cyclohexane, you will see actually one most important thing is that when lambda max is what maximum wavelength which is going to be absorbed by a particular compound. So lambda, this value of lambda max will increase, means energy will going to be decreased when there is a conjugation in the compound. So when there is increase in conjugation, then consequently the lambda max value will going to be increased. So you will see here that if in this example here 1,5-hexadiene, here there is absence of conjugation, while 2,4-hexadiene there is conjugation. So lambda max value is, you will see the trend, lambda max 178 for 1,5-hexadiene and 227 for 2,4-hexadiene. So you have seen the trend of conjugation, the effect of conjugation. This is again another example. Now auxochrome. What is auxochrome? Auxochrome is actually not responsible for color, but it is a group when it get attached with the chromophore, then it will this chromophore will show color. And the auxochrome groups are here in this example, the auxochrome groups are hydroxyl groups and amine groups. You will see benzene has a lambda max value 255 nanometer, and when a functional group OS get attached to this, then the lambda max value get increased, and further for amino it get another increment to 80 nanometer. So what is the trend of auxochrome? It increases the lambda max value as the conjugation increases the lambda max value, and thus auxochrome and chrome 4 you have seen. Now absorption and intensity shift. 4 types of shift are seen in the UV visible spectroscopy. The first one bathochromic shift, and the second one is hypsochromic shift, and the third hyperchromic shift and hypochromic effect. The first two, bathochromic shift and hypsochromic shift, are shift in wavelength. Means if there is for any reason, for some reason, if there is a shift in wavelength from lower to higher value, then it is called bathochromic shift. And you have seen before some time, you have seen that conjugation and auxochrome increases the lambda max value, so it causes bathochromic shift. Similarly, hypsochromic shift is the shift when any effect when any effect causes reduction in wavelength, then it is called hypsochromic shift. Means if the conjugation, if by any reason conjugation get decreased in any compound, then it will cause hypsochromic shift or blue shift. Now this is an example. And the third one is hyperchromic effect. Means when the intensity of radiation get increased, then it is called hyperchromic shift. Auxochrome also causes a hyperchromic effect. You will see here that in case of pyridine, the lambda max value is 257 nanometer, while when alkyl group, methyl group get attached to the position second, then 2-methyl pyridine have lambda max value 260 nanometer. So this is the example of hyperchromic effect. And the next one is, the last one is hypochromic shift. Means when by any reason there is reduction in intensity, then it is called hypochromic effect. So here you will see in case of naphthalene, the extinction coefficient actually is extinction coefficient is actually the measure of intensity. The more will be the value of extinction coefficient, the more will be the value of extinction coefficient, the larger will be intensity. So you are seeing here that naphthalene extinction coefficient is 19,000, while in case of its alkyl substituent it is 10,000 to 250, means almost 900 extinction coefficient get reduced. So this is the example of hypochromic effect, and the next one, this is the schematics of shift. You are seeing here this is the bathochromic shift, and this is the hypsochromic shift. This is hyperchromic shift, and it means this is intensity variation, extinction coefficient measure the intensity, and this is the shift in wavelength. So now, what is effect of solvent in UV visible spectroscopy? You have seen two type of, actually out of 4 allowed transitions, means n to pi star, pi to pi star, sigma to pi star, and to sigma star. 2 transitions, n to pi star and pi to pi star transitions are occurring only when there is a non-bonding electron and unsaturation in compound. So when these transitions will occur, then certainly there is a presence of unsaturation in compound. And sigma to sigma star transition and n to sigma star transition are not much informative. So these 2 transitions, n to pi star and pi to pi star transitions, are most informative in visual spectroscopy. Now we will see the effect of solvent in these 2 transitions. So we know 2 types of solvent, the protic solvent and non-protic solvent. So in case of pi to pi transition, the protic solvent stabilizes the excited state, means pi star energy level. So what will happen? It goes down. So the separation of energy, what will happen? Separation of energy will be reduced. So when separation of energy will reduce, what happen? The wavelength will increase. So in case of pi to pi star transition, protic solvent causes increment in wavelength, and aprotic solvent causes reduction in wavelength. So, and the next one, in case of n to pi star transition, what happens? The protic solvent stabilize the ground level, means non-bonding energy level. So what happens? The energy level, non-bonding energy level, will get decreased. So what happens? The separation between n to pi star transition will be increased, and so this causes the reduction in wavelength. So what we have seen? We have seen the protic solvent causes wavelength increment in wavelength in n to pi to pi star transition, while decrement in wavelength in n to pi star transition. Now coming to the lambda max calculation has been performed by Woodward-Fisher rule. So What is Woodward-Fisher rule? Actually, Woodward and Fisher have given some numerical value for the some classification. You will see here for the they are classified as homonuclear and heteronuclear. So what happens in case of homonuclear? What is homonuclear? When the both double bond are present in same cycle, then it is called homonuclear. And when the both double bond are in separate cycle, then they are called heteronuclear. So next, now what is exocyclic bond? Actually, we are talking about these terminology because Woodward-Fisher had given some numerical value of lambda max for these classified compounds. So what is exocyclic double bond? When the double bond is outside the cycle, then it is called exocyclic. This is exocyclic, this is exocyclic, and what is this? This is endocyclic. So you have seen the exocyclic and endocyclic double bonds. Now for the acyclic heteronuclear conjugated diene, the parent value of lambda max is kept 215 nanometer. For homonuclear conjugated, it is 253. Acyclic trienes 245. Now these are the parent values, and for additional increment means if there is substitution of alkyl group or ring residue, here these for this exocyclic bond, these two are ring residue, and for this exocyclic double bond, these two are ring residue. So these are additional increments. So for each increment, there are lambda max value additionally given. For alkyl substituent or ring residue, the value is 5 nanometer. For exocyclic double bond, value is 5 nanometer. Again, for double bond extensing conjugation means if this is the double bond and this is extensing the conjugation. So for this, in this case, the value will be 30 nanometer. If there is a oxochrome, then these are the values. Now we will see an example and we will calculate the lambda max value. This is a example of homonuclear double bond. Now the value for parent value for homonuclear double bond diene is 253 nanometer. There is you are seeing two alkyl substituent. The two alkyl substituent are one is here, one is here. These causes additional lambda max value 10 nanometer. Now there is two ring residue, but where is the ring residue is present here, here and here. Two ring residue. So this is this causes additional value of 10 nanometer. So we will add these increments to the parent value, and this will give you value 273 nanometer. This is the calculator value of lambda max, and this is one of example for lambda max calculation using Woodward-Fisher rule. So you can calculate lambda max value by using this parent values and increments, and you will see experimentally the value of lambda max will be near about more or less it will be near about the calculated value. So you will I expect that you will solve another example from your textbooks, and you will be more familiar. Now solvent effect intensity. This is some value of lambda max and extension coefficient. You will see here the schematics. These are some value. This is for your knowledge when you are going to perform the UV visible spectroscopy. And now I am expecting that you are benefited with this lecture, and if there is any query, you may contact me. Thank you.